On, right. And do you have like a, this is the pointer?
Yes.
Okay.
Yeah.
Okay. Is this the right way? And then I need to check whether this is the right talk. Okay. Sorry?
I'm really looking forward to it.
Thank you very much.
Hope we talk after.
Sorry?
Sometime. I hope
Yeah.
that we can talk after.
Yeah, definitely. Yeah, thanks.
Say your last name for me.
Nopenai.
Nopenai.
But you can also say no penny.
and Uta is right.
Uta,
Yeah.
Uta Nopenai. Yeah, excellent. Thanks.
All right. Welcome back from lunch. Hopefully everyone had a delicious meal and is ready for the afternoon session. So the format for the afternoon will be familiar. It's just like the morning, a talk, followed by a coffee break and a poster session, and then followed by a talk, and then it's aperitivo hour. So our first talk of the afternoon is Uta Nopenai. Delighted to have you. Thank you.
Okay. Thank you very much for the kind introduction and the invitation. So it's really great to escape the gray sky from Birmingham. See what you hear. So in our natural environment, our senses are constantly bombarded with many different signals. Buzzing sounds, lightning flashes, the smell of chestnuts. To make sense of this cacophony, the brain should, the brain should integrate signals coming from a common source, but segregate signals coming from different sources. Multisense integration is critical for our daily interactions. First of all, it increases the bottom-up salience, and this is important for detection tasks. And secondly, it increases the reliability of the representation, and this is important for estimation and discrimination tasks. Now, while it was traditionally believed that multisense integration emerges only in higher order association areas, over the past decade, there has been some sort of revolution, maybe not, but at least like a sort of, the views have been altered, and it's now evidence from neuroanatomy, from neurophysiology, as well as from neuroimaging, demonstrated that multisense integration emerges already here at the primary cortical level. And this, of course, then raises the question, well, if perhaps the entire neocortex is multisensory, as Charlie Schroeder and Asif claimed in one provocative paper, what then, how then do we define an area, right? Then multisensory is no longer informative. And that's what is sort of like one aim, also like to move beyond saying an area is multisensory and defining what are the different roles. Now, the talk falls in 3 parts, and the third part you can sort of bear in mind because you can vote on this. The first one will be about temporal binding and predictions to link nicely with the work by Richard, and then we move on to Bayesian causal inference, and the third part can either be Bayesian causal inference, learning and adaptation, or you can go for something which is like layer-dependent activations where we use FMI at 70 to characterize multisense integration in different layers within the cortex. So that's something to bear in mind. In the end, you can decide on that. Good. So, inspired by the sort of like idea that the brain is indeed like, also like from predictive coding models, right, is indeed trying to predict the world out there and the sensory signals that are coming in, we thought, how does the brain really decide and determine whether 2 signals come from a common source and should be bound together? And we thought that probably, even though most of the work has been focused only on the visual system, it's not only that the brain needs to predict the signals in one particular system, but it also needs to predict the sensory signals across the different areas. And so we were thinking that perhaps temporal predictions also enable the brain to determine whether or not 2 signals come from a common source, because if they are coincident in time, if they are synchronous, it's more likely that they are generated by a common source. And to address this question, we basically presented participants with naturalistic stimuli, so either speech stimuli or piano music, and they were either synchronous or they were auditory leading. So you see, basically, you first hear the signal and then you basically perceive the mouth movement opening, or they were visual leading. And we presented the 2 different levels of asynchrony because we thought that the prediction is basically like, if the visual signal or the auditory signal, if the auditory signal comes in first, then the auditory system would generate predictions that are sent to other sensory systems, so that then the lagging signal would generate a prediction error signal in the visual system. And conversely, if the visual signal is leading, you would observe a prediction error signal in the auditory system. Now, prediction error signals generally are sort of associated with activations for asynchronous relative to synchronous signals. So hence we would expect that auditory leading signals lead to enhanced activations in the visual system, while visual leading signals lead to activations in the auditory system. And this is exactly what we observed both for speech as well as for music stimuli. So when you look at visual leading relative to synchronous, you observe increased activations in the auditory system, while if you look at auditory leading relative to synchronous, you observe enhanced activations in the visual system, in particular in area V5. So it generalizes across the 2, actually even 3 stimulus types. We also had like sine wave speech on top of it. So this suggests that the leading signal forms the initial predictions that are then violated and that are then sent over to other sensory systems and that are violated by the lagging signal, and this would lead to cross-modal prediction errors. And next we asked, well, can we also train temporal predictions? In particular, can we train temporal predictions for something which is basically actions, right? We either have speech actions or we have music actions. Now, we are all speech experts, unless you talk about like different languages, but only some of us are sort of pianists, and we didn't have quite Brendel in our scanner, even though I would have loved to have him in our scanner and also giving a piano concert. But we just had like students that either were piano amateurs, pianists, or they were just like typewriters, right? They were just like typing basically constantly. And the idea was that if training the temporal predictions relies on a sensory motor system, so in particular like on the sort of cerebellar premotor circuitry, which might sort of like be a forward motor that generates predictions about the sensory consequences, which in our case are both visual as well as auditory, because you see the movements as well as you hear the tones generated. Well, if it relies on such a system, then you would expect that musicians are better in making temporal predictions for piano music, but less so for speech. And this is exactly what we observed. So on the left, you see basically the speech signals, on the right, the piano signals, and on the x-axis, you have the different levels of audiovisual asynchrony, and on the y-axis, whether the proportion of trials perceived as synchronous. And first of all, you see that, of course, the greater the synchrony, the asynchrony, the less likely they are perceived as synchronous. But what is more important is that there's basically a fine-tuning of this sort of asynchrony curve for musicians relative to non-musicians, and that's predominantly here for the piano music and only non-significantly for the speech signals. So at the behavioral level, this suggests that indeed learning piano enables the brain to make more precise temporal predictions, not only in one modality, but across multiple sensory modalities, allowing participants to be more precise in judging two signals as being asynchronous. Now, on top of it, we would have expected that these asynchrony responses are increased in the cerebellar premotor circuitry, and this is indeed what we observed. Here it's predominantly on the left side, but we found non-significantly also responses on the right side of the cerebellum, and here in the premotor circuit. Moreover, in the premotor cortex, we also observe, specifically for the musicians, increased asynchrony responses selectively for piano music stimuli, the more precise, so the narrower this curve. So the more precise participants are at determining and at detecting audiovisual asynchrony, the greater these asynchrony responses in the premotor area. So to summarize, in the first experiments, we demonstrated that auditory leading and visual leading signals lead to prediction error signals in different brain areas. So basically, an auditory leading signal generates predictions within the auditory system, and thereby prediction error signals increase responses in the visual cortex and vice versa. In the second part, in the second experiments, we've then demonstrated that at least for action stimuli like music or speech, we can fine-tune and train this circuitry, and this leads perhaps on a forward model which might be instantiated in the premotor cerebellar circuitry. So this might be a supplementary mechanism for making temporal predictions even in perception. And this supplementary mechanism can be fine-tuned via experience-dependent plasticity. Of course, we need to sort of follow this up by additional experiments, demonstrate that it's experience-dependent plasticity and not just, for instance, genetic effects, that the people that play piano are sort of also more talented at those things. Good, so this first part has focused on temporal synchrony as a very important cue which informs the brain whether or not two signals come from a common source or come from different sources. But of course, another important cue is spatially co-location. So if two signals are at the same location, like right now, I'm talking, well, actually right now it's probably, no, are there loudspeakers somewhere? Yes, probably there, right? So like, right now, actually, it is the ventriloquist effect, I should say, because it is not really at the location, at the same location, but you still bind. And that's actually the next thing you can also think about. The next section is about the ventriloquist effect. But generally, you would think if you see something on the right and you hear something on the left, you would actually not bind those two signals. Now, let's go through this in detail. So let's assume you're a young, energetic ornithologist running through the forest, trying to make the most precise sound recordings and the best pictures of birds. And you suddenly spot this little robin sitting on the branch. In addition, you hear a little robin singing. I'm not going to present how this works, but roughly, right? Okay, good. And so now the question is, how should you direct your microphone and how should you direct your camera? Well, it depends. It depends on the causal structure of the world. And there are two fundamental hypotheses that the brain should entertain. First of all, there might be one robin sitting on this branch, and the same robin is also singing. Now, if this were the case, what the brain should do, this is basically how you can formalize this in a sort of graphical model. You have one underlying source, and this underlying source generates a visual signal, and it generates an auditory signal. Now, if this were the case, what the brain should do is basically it should integrate the two signals, which we call XA for auditory, XV for visual, weighted by their relative reliability, plus add some prior, but we ignore that here. And that gives you the most precise or most reliable estimate of where basically this bird is located. And that's basically sort of maximum likelihood integration, right? Maximum likelihood estimation. But there's a second hypothesis, and that is that there's one robin that you see sitting on the branch, but there's a little robin hidden in the bush that you can't see, but that you hear. Now, if this were the case, integrating these two signals weighted by their relative reliabilities would be rather suboptimal, because then you might take a picture right of this spot, right? And then at the end of the day, you look at it on the computer screen and you see that there's no robin in the picture. Rather suboptimal behavior. So what should you do in that case? Well, in that case, the model is you have one robin that you can see. So one robin is one underlying source here. It generates the visual signal. And another robin is another underlying source that generates the auditory signal. And if this were the case, if you want to direct your camera, you should only take the visual signal. And if you direct your microphone, you should only use the auditory signal. So that's demonstrated here. So you would actually use two different equations. Now, the problem, and this is sort of like the full segregation model. I should probably also add, this is the forced fusion model, and this is sort of the maximum likelihood estimation model which has dominated the multisense integration field over the past decade. It had basically ignored that there might be two different models. So, okay, we have the forced fusion model and we've got the full segregation model. Now, the problem is that the brain does not know, right, whether this is the correct model of the world or this is the correct model of the world. But it needs to infer this from the sensory signals themselves. For instance, them being correlated in space, correlated in time, or I mean like co-located in space, correlated in time, maybe being semantically, having the same semantically similar features, etc. And based on those cues, sort of sensory correspondences or higher order correspondences, it can then compute a so-called posterior probability that this is the correct model of the world or that this is the correct model of the world. And then it needs to account for its uncertainty about what is now the right model of the world by doing something which is called, for instance, model averaging, but you could also use different decisional operations. So model averaging is that if you want to direct your microphone, you take the forced fusion estimate, this yellow one, and the full segregation estimate for auditory, so this green one, you weight them by how likely that this or that this model is the correct model of the world, and this gives you the location for your auditory estimate. And for your camera, you would basically take this plus the red one. Good, so what would we predict? Now, let's make a very simple experiment. We present the sound always from the center, and the visual signal from various audiovisual spatial disparities. And that's here along the x-axis. Now, if you were able to selectively focus and point to the sound, you would always point to 0, right? Because it's always at 0. If you go completely with the visual, something which people call visual capture, you would do something like this. If you did something like the dominant forced fusion model would predict, it's still a linear equation, so you would basically go like this, right? You do like a weighted integration of the two. If you did something like Bayesian causal inference, then you would first go more with the visual, because at the beginning it's quite likely that the two signals are coming from a common source, so you integrate them. But the larger the spatial disparity, the less likely it is that you integrate. At some points, integration breaks down, and basically you point to the auditory signal. And this is roughly what we observe, in particular when the auditory signal is reliable. So first you go with the visual, but then at some point integration breaks down. And in later experiments, we really demonstrate that if you go via like 50 degrees and you have really good subjects, then indeed you don't have any integration anymore. So what we basically demonstrate that the brain arbitrates between information integration and segregation as a function of spatial disparity. Good. So what we've demonstrated so far is that this model sort of makes roughly sense, right? It's sort of intuitive. Secondly, it's also quite a good predictor for participants' behavior. The next question that we want to ask is like, okay, just because it's a good model of behavior, right, does it have to do anything with the brain? Can we somewhere in the brain find estimates that are sort of, or regions that encode these estimates, like the forced fusion estimate, the full segregation estimate under visual, the full segregation estimate under audition, and this sort of model averaging estimate? And for this, we put people into the scanner and present them with beeps and flashes or blobs, basically from 4 different locations, the auditory, and 4 different locations, the visual. So this gives us a 4x4 matrix along the diagonal. They are audiovisually co-located. The more you go off diagonal, the greater the audiovisual spatial disparity. In addition, we manipulate the reliability. So it's either like 2 degrees, so that's the reliability of this visual cloud. So this is a reliable cloud, and this is an unreliable cloud, because you don't have a clue really where the visual signal comes from. And moreover, we ask participants to locate either the auditory signal or the visual signal. Now, note that under forced fusion assumptions, you would assume these are identical. People give you the same response, right? Because under forced fusion assumption, it's just one source, so you don't have any differences. Good. So what we basically manipulate implicitly is audiovisual spatial disparity. So what we next did, we then fitted this model to participants' behavior inside the scanner, but participants' localization responses. And from this, we obtained these 4 different estimates for every single trial. And then the next step, we then asked, okay, where does the brain encode these spatial estimates? And we asked this along the visual processing stream, so the dorsal visual processing stream, as well as here along the auditory processing stream, like going into the planum temporale. And how did we do this? Well, we use support vector regression because it's a continuous space, right? And we asked, like, okay, where are they predominantly encoded? So we computed basically exceedance probability. So we have here along the x-axis V1 up to IPS4, and here you have the auditory areas, primary auditory area, higher auditory areas. So what we find is that, first of all, not surprising, but rather reassuring, if you're in visual areas predominantly encode the visual estimate. Auditory areas predominantly encode the auditory estimates. Okay, not very, very surprising, but reassuring that we are not doing some complicated analysis which doesn't tell us anything. But what is exciting is what happens here in the parietal cortices, while the sort of more posterior areas, IPS0 to IPS2, encode predominantly something like a forced fusion estimate, so it integrates the 2 signals irrespective of how far they are in space, and irrespective of whether they have to report the auditory or the visual signal. Here in this sort of more anterior area, in particular IPS4, that does something like model averaging, right? Basically, IPS4 arbitrates between information integration and segregation as a function of the underlying causal structure of the world. So cortical hierarchies perform Bayesian causal inference by, well, I wouldn't say simultaneously, by encoding multiple spatial estimates, primary sensory areas predominantly segregation, IPS1-2 predominantly forced fusion, and IPS3-4 predominantly something like Bayesian causal inference. So IPS3-4 forms a spatial estimate that takes into account the uncertainty about the causal structure of the world. Now, we were quite happy, right, especially when the paper was published, but of course, we were not colorblind, right? We were happy that the reviewers seemed to be colorblind. They didn't point it out that this is not red and this is not green and this is not blue and so on, but there's all a mixture of different things. So one worry with model-based analysis is always that you look at your data only from the perspective of your model. So you might miss out on something. In particular, if you fit like a sort of crap model to your data, you still get the best model out. So what we thought is, okay, let's maybe look at the same data again, but now from a sort of, I call it model-free, but of course there's nothing which is model-free, but it's sort of like more factorial analysis design. So basically we could say this is a 2x2x2 factorial design. One factor is being spatial disparity. Things are close together in space or far apart in space. The next thing is visual reliability, and the third one is whether the auditory or the visual signal is task relevant. And what we then did, we basically predicted participants' localization responses by the true auditory, the true visual locations separately for these 8 conditions. So for basically all these 8 conditions in our 2x2x2 factorial design. And this gives us 16 beta weights, and then we form basically an audiovisual weight vector, which is between 0 and 90 degree. 90 degree telling us it's pure visual influence, 0 degree, it's pure auditory influence, and everything else is a mixture of the two. And what we observe here is, in dark, for visual report, you see there predominantly, when people report the visual location, their perceived location is dominated by the visual signal. It's 90 degree, right? While for auditory, it's not just 0, but it's sort of in the middle. But what is more interesting is that we also found an effect of reliability. When the reliability, the visual reliability was high, then the weight of the visual signal was stronger in their perceived location. And this was predominantly the case for auditory, but also for visual. Furthermore, we also observed an effect of disparity. So when the 2 signals were close in space, like here, small spatial disparity, you have more integration going on than when they are far apart in space. And what is most important, we also find this interaction which we would expect under Bayesian causal inference. So under Bayesian causal inference, you would expect qualitatively a profile that the difference between auditory report and visual report is large when the 2 signals are far apart in space, right? Basically, when the signals are far apart in space, you can more selectively report and attend to the auditory or to the visual signal. So, how do we go from there? Next, we basically trained a support vector regression model on the congruent trials from activation patterns, basically, to the outside world. So this training basically allows us to get a mapping from activation patterns to locations outside in the world. Because for congruent trials, we know where this thing is. And then we generalize to the incongruent trials. So basically, we decoded where does the brain area believe that a stimulus, where the visual is, for instance, at -3 and the auditory is at +3, where's that located, right? From this, basically, we now got like location responses from every single brain area. And now we use the same trick that we use at the behavioral level, and we ask like, okay, these decoded location responses, how much are they influenced by the true auditory and the true visual location? And this gives us, again, an audiovisual weight vector. And again, not surprisingly, but more reassuringly, if you look into the decoded responses in visual areas, they're predominantly focusing, or they predominantly rely on the true visual location. In auditory areas, they predominantly rely on the true auditory location. But the exciting bits happen here in the higher order areas, where indeed you find like reliability weighted integration. So this IPS areas basically functions like a visual area when the visual signal is reliable. But when the visual signal is unreliable, it's also influenced by the auditory signal. Next, we focused on the effect of task relevance. And again, the interesting bit happens here in higher order auditory areas and in parietal areas. So the visual areas, the IPS, they acted again like a visual area when the visual signal was task relevant, but it was more strongly influenced by the auditory areas when the auditory signal was task relevant. So this suggests that IPS integrates auditory and visual signals weighted by the bottom-up reliability as well as by the top-down task relevance into spatial priority maps. And moreover, we also found this sort of important qualitative task by discrepancy interaction. So audiovisual signals were integrated when the two signals were close in space, but they were more segregated when they are more far apart in space, in IPS 3-4. So here, spatial disparity basically determines whether or not two signals are integrated. And this basically contrasts with sort of the effect of spatial disparity that we found in primary sensory areas. Because in primary sensory areas, you also effect of spatial disparity, but basically, here it's not that spatial disparity does not determine the role of the task irrelevant signal, as it does here, but it determines the role of the non-preferred signal. So in primary visual area, spatial disparity determines whether or not the auditory signal has an influence on the decoded location, and in auditory area, whether the visual signal has an influence on the decoded location. So basically, spatial disparity determines the effect of the irrelevant signal in IPS and the effect of the non-preferred signal in low-level primary sensory areas. So to basically summarize from this slide, what we find is that for IPS 3-4, we said before, it's basically it's the region that performs something like Bayesian causal inference. And now from a qualitative perspective, we can link it back to the sort of classical literature. We can say, yes, it forms spatial priority maps that integrate sensory signals weighted by the bottom-up reliability as well as by the top-down task relevance, whilst at the same time taking into account the uncertainty about the causal structure of the world. So next, we basically asked, can we also track these neural representations over time? And for this, we basically used EEG. And I have to say, so far I can only show you the topography results. We haven't gone to source space yet. So basically, you see here, like for the unisensory conditions, you see the different locations. You see already by eye that yes, from the topography, you can already see that the topography differs across the different locations. And first of all, what we looked at using this sort of like temporal generalization method, when do we observe spatial representations that generalize across sensory modalities? And that's what you can see here basically emerges a little bit at 200 milliseconds, but predominantly from 300 milliseconds onwards, do we have representations that we can decode from auditory to auditory, from visual to visual, but also from visual to auditory, as well as from auditory to visual. So here are sort of like representations that might be more amodal, right, later on in space, later on in time. Next, we ask, can we apply the same analysis strategy that we used for fMRI data now also for EEG data? So we basically first, we trained on audiovisual congruent stimuli, and we generalized to audiovisual congruent stimuli first. And this demonstrates that the topographies are relatively dynamic, right? They change because so for people that might not be so familiar with these temporal generalization methods, basically what you do is you train on every single time point and then you generalize to all other time points. Now, if you only have like a nice diagonal matrix, it means that the representations are very dynamic, right? You can't generalize at all. If you get something which goes here to the off-diagonal, that means you can generalize over time. That means the topographies are more stable. And you see that basically this is sort of relatively dynamic, right? And then we basically also trained on the congruent trials and we generalized to the incongruent trials. Now, exactly as with FMI, we now asked and we decoded where does the brain, when does the, instead of where in FMI, we now ask when does the brain believe, where does the brain believe that a stimulus is located at a particular time point? So we used the same trick. We basically generalized to the incongruent trials, and then we predicted those decoded locations by the true auditory and true visual locations. This gives us, again, like an audiovisual weight vector. And now, as in fMRI, we now ask, like, when does the effect of reliability occur? It occurs roughly from 100 milliseconds onwards. So from 100 milliseconds onwards, these decoded representations are influenced by the true visual and the true auditory location weighted by their relative reliability. The effect of task relevance emerges later on, here at 200 milliseconds, which was sort of later, which was located in higher order association areas. And finally, where's this task by disparity interaction, which is sort of like the qualitative profile that we should expect for a region involved in basing causal inference, and that is basically here from 300 to 400 milliseconds. We observed the same profile that we observed in IPS 3.4. So to summarize this whole multimodal experiment, what we've demonstrated is cortical hierarchies perform basing causal inference by encoding multiple spatial estimates. So depending on which area in the brain you ask, they give you different responses on where they think the stimulus is located, right? The visual give you more the visual location, the auditory more the auditory, and the IPS and higher order planum temporale, they do some sort of weighted integration. And in particular, I'd like to focus on the area IPS 3.4 because this really performs Bayesian inference in the way that it integrates sensory signals weighted by the bottom-up reliability and top-down task relevance into multisensory spatial priority maps that take into account the uncertainty about the world's causal structure. And this happens at about 300 to 400 milliseconds. Now, so far, I focused on sort of like implicit causal inference, right? So people were not explicitly asked, do two signals come from a common source or not? But the implicit causal inference was important for them to generate spatial representations. In the next step, we asked, like, okay, can we also explicitly ask people whether or not they think the two signals come from a common source? And for this, we have a design where basically the auditory signal was left or right, the visual signal was left or right. And from this, you also have like physical congruency, right? So physical congruence is when the visual is on the left and the auditory is on the left, and here you have the incongruent ones. Now, on top of it, participants responded every time whether it was congruent or incongruent, so common source or not. And so we also have like perceptual congruency. And finally, in order to dissociate participants' responses from their perceived location or for their perceived common source causal structure, we also changed whether they had to respond with their left or with their right hand. And also like the left or right, left or right hand. Now, because we wanted to have all this nicely orthogonal, or I should like Aggerstrand, put a great deal into fine-tuning using like a quest procedure, basically a staircase procedure, very nicely fine-tuning that we roughly had like 60–70% of perceptually congruent and incongruent stimuli, responses for the different stimuli, right? So this allowed us then later on to really think of those four factors as being orthogonal. And then what we did next is now we wanted to decode where can we decode auditory location, where can we decode visual location, where can we decode physical congruency, perceptual congruency, and motor response. Now, let's first start with the visual location. Not surprisingly, right, you can decode this from visual areas. Auditory location, not surprisingly, you should be able to decode them from planum temporale, and indeed we can. Then I should maybe say first the motor responses, not surprisingly, Oh, where's this? The motor responses can be decoded from the pre-central gyrus. But what is interesting is like where can you decode the physical congruency? So the physical congruency you can decode already like here from planum temporale, but in particular again from this sort of IPS 02 as well as from the frontal eye field. And the perceptual congruency you can also decode, again from this circuitry, from the parietal cortices as well as from the frontal eye field. Critically, the causal inference, the perceptual congruency predominantly peaks here in the dorsolateral prefrontal cortex. And so what we would suggest is that the dorsolateral prefrontal cortex computes the final causal inference that influences then top-down modulates the spatial representations that are formed, or spatial priority maps that are formed in the sort of parietal areas or in this frontoparietal circuitry. What is also important to notice that this frontoparietal circuitry is also top-down modulated also by participants' motor response. So basically, the frontoparietal circuitry forms a circuitry that integrates audiovisual signals weighted by their reliabilities, is informed by the causal inference that is finally obtained in the dorsolateral prefrontal cortex, and translates this into motor responses, basically, and is also feedback modulated by this. Yeah?
Say again the difference between physical congruency and perceptual congruency.
Sorry, say you?
What's the difference between the two?
Okay, physical congruency is whether or not the two signals are congruent or incongruent. Perceptual congruency is because we have them at really like at 2 degrees, right? So it's like there's a lot of uncertainty, and that's why also our decoding results are so small, right? Because basically participants are really quite unsure whether it's physically congruent or incongruent. And then perceptual is what they really perceived. And then we also dissociated what they perceived from what they responded by making sure that sometimes they responded with their left hand and sometimes they responded with their right hand, so we counterbalanced this as well. And so during our decoding, we made sure that we downsampled our trials so that they were completely uncorrelated and orthogonal, so that we can really say this is whether participants thought, perceived congruency is whether or not they thought and make the decision it was congruent or incongruent. Physical congruency, whether indeed they were congruent or incongruent, and they are sort of orthogonal in this case. And so, and in this way, it is interesting that here, the peak of the perceived congruency comes in the dorsolateral prefrontal cortex. Now, of course, I don't think that the brain waits until 400 milliseconds, right, before it starts binding on unbinding to sensory signals. But my view is that there are multiple different types of congruency cues that become available at different times. So, for instance, initially you have temporal coincidence at the very first and the most dominant congruency cue. But later on you have spatial congruency cues, right, which, of course, because auditory and visual space are encoded differently, right? You have different reference frames. There might be sort of intermediate reference representations, as Jennifer Groh showed in neurophysiology. So this is like a cue which comes later on. Let's assume we had like semantically invested stimuli, right? Whether something is like a dog or a cat is certainly later. So all these cues become available at different time points. And I suspect that the DLPFC accumulates this all of the time. But I don't think in a sort of simple feed-forward model, but I think it's more like in a loop thing, right? Basically, these signals, or these areas already start like binding and unbinding. They send already based on the cues they process, they send the information to higher order areas in DLPFC. And then depending on what the DLPFC thinks, it sends it backwards, and that sort of refines the process. So I think about it like you have a feed-forward, feed-backward loop, and thereby the causal inference becomes progressively refined, while at the same time the causal inference determines what you perceive, right? It's not only like the spatial representation is not only weighted to cue integration, but also when you make speech integration, right, as illustrated in the Magwerk effect, for instance, or also you could also, for instance, morph one object into another object. So it's just a very basic thing. But the thing is, there are two decisions that sort of mutually are independent. One is you need to generate a percept about what you see or where you see it, like an estimate about something, and this is determined or dependent on whether the two signals do not come from a common source. And they're sort of like, I think one basically depends on the other, and you need to sort of update these two things. And what we try right now is, for instance, doing like an accumulation of evidence model where indeed we check like, okay, how do the two decisions, causal inference as well as spatial estimate, basically get refined over time. Does that make sense? Yeah? Yeah.
Point of clarification. I don't understand why responding with your left hand and right hand associates perceptual
Okay, so basically, maybe I should have phrased it like this. So the mapping to the response was orthogonalized across different sessions, across different blocks. So sometimes when they thought it's perceived as congruent, you responded with your left hand, but in another block you responded with your right hand. And so therefore, later on we could ensure that it's not just a response mapping. Yeah, does that make good? Yeah, so and in this way we can really say, okay, we have a motor response, and that's also why it nicely dissociates here, right? Because otherwise in DLPFC, if it sort of like encodes perceived congruency, it should also encode the motor response, and it does not. So in this way, that's nice that we really were able to dissociate the two. But on the other hand, it's then also nice that now when we have our motor response encoding also here in parietal cortex, this cannot be just like be explained by the fact, well, you know, obviously because it encodes perceived congruency, then it should also encode motor response. But it really means that it's sort of like, I think this region is really like, I mean, as also other literature suggests, right, it's really like a key region which sort of transforms sensory inputs into representations and translating it then in motor responses. Good, so cortical hierarchies perform Bayesian causal inference. IPS34 integrates sensory signals weighted by the bottom-up reliability and top-down task relevance into multi-sensory spatial priority maps that take into account the uncertainty about the world's causal structure at approximately 300 to 400 milliseconds and is informed also by the explicit causal inference in DLPFC. So now how am I doing this time? Am I still allowed to say something? Okay, so what would you prefer? Would you prefer layer-dependent profiles, or would you form at 70, or would you prefer Bayesian causal learning and adaptation? A learning perspective or a layer-dependent, cortical layer-dependent profile dependent? Okay, who's for the learning? 1, 2, 3. Okay, who's for the layer-dependent profiles? Less. Okay, we go with the learning. Sorry. The rest can come in the break. And of course, now the majority that didn't vote at all, right? That's always like in democracy, I'm sorry. You know, whether it's Brexit or whatever, you need to go and vote. Whether you go for Trump, everyone that didn't vote has to suffer, basically it. Okay, Bayesian causal learning and adaptation. Now we've had this model, and there are various parameters. So one parameter is, for instance, you have and these parameters are like, for instance, the prior, right? You have a prior expectation whether or not two signals should be bound into a common source. So for instance, right now, I'm the only person predominantly talking in this room, right? And so you probably integrate what I say with who's standing in front of you. But if you are in a busy pub, especially in a UK pub, right, in a London pub, right, it's very busy, well, there's no smoke anymore. But anyhow, so it's a busy pub, and now you need to learn, like, should you integrate or should you not integrate? And there, you're probably less likely to integrate because there's so many different voices, right? And that means that, yes, you have some expectations, and can we manipulate those? And what we did here is basically, it's a simple behavioral experiment where we presented participants with basically, again, our sort of like boring audiovisual signals, and they were either temporally synchronous and slightly spatially disparate so that we could measure a ventriloquist effect, or they were asynchronous. And what we did, we sort of manipulated over time the context, which means the percentage of those asynchronous relative to the synchronous trials. And what we would expect is, if you're presented with many asynchronous trials, even for the same physically identical signals, you should be less likely to bind them, and hence the ventriloquist effect should decrease. And this is exactly what we found. Basically, this shows like the contextual difference, so how much more do you perceive a ventriloquist effect when you are presented with more temporally synchronous stimuli relative to asynchronous stimuli. And you see that basically, yes, you're more likely to perceive a ventriloquist effect. Next, we did the same thing also inside the scanner, but because the ventriloquist effect inside the scanner is a little bit temperamental, we used the Magwerk effect. And it's the same rationale. So we either have Magwerk stimuli amongst many incongruent stimuli, or we have the Magwerk stimuli amongst many congruent stimuli. So this is a GU with a GU, and here we have a bar with a GU, and then we get like a P and key, which should give you a Magwerk percept of a T. So, and then what we looked at, basically, we looked at how often do you perceive a Magwerk effect, which is like basically the fused percept, or how often do you have like an auditory selective, auditory segregation, so that you basically report a pa rather than a ta. And you see that basically you are more likely to see a Magwerk effect when you are in the fused context, so when you're in a context with many congruent stimuli, while you have more auditory responses, so you're more likely to perceive pa when you are in the context with many incongruent stimuli. So again, at the behavior level, it nicely corresponds to what we perceive, what we saw in the other experiment. You are more likely to integrate or fuse signals into a Magwerk effect or into a ventriloquist effect. And at the neural level, this is basically reflected here in this sort of dorsolateral prefrontal cortex, in particular in this inferior frontal sulcus and going into the inferior precentral sulcus. And you see that basically you have more activations in this area when participants perceive pa, so when you segregate. And this segregation is also, and that's reflected here in the interaction, modulated by the context. So in particular, it is up-modulated, this difference, when you are in an incongruent context. So when there are many incongruent stimuli, you expect that you need to segregate, you get more activation in this region, and this also amplifies then the difference between whether you perceive an auditory or the fused percept. So common source prior adapts to probability of the congruent stimuli, and this was reflected in the dorsolateral prefrontal cortex. And the final, just what I want to quickly highlight, is there's something else which you can also learn over time, and that's actually, I'm quite excited about this, because so far, all multisense integration models that I'm aware of assume that the brain knows already the sensory reliability of the signals, right? So far I've always said, well, you know, you weight the signals by their reliability. But the question is, how does the brain know it, right? How do you know when you're in a sort of like context, what is the reliability? So far, all models assume it's instantaneously known. And what we've been thinking is, well, is that really the case? Do you not need to learn the reliability over time? And can we find this effect? And what we did here is, again, our boring like flash beep experiment, where we manipulated now the reliability of the visual cloud over time. And this was continuously always at sort of like, so I think every 100 milliseconds we had like a visual thing flashing. And only now and again you have also a sound together with this. And what we would expect is that based on over time, you would learn the reliability, and the ventriloquist effect would be then dependent on not only the reliability when the sound was presented, but also the reliabilities beforehand. And so we manipulated this in a sort of like once in a sinusoidal fashion, so it was going up and down, and was going up and down constantly, right? It's just now that we basically chopped these time series apart and then averaged them, so that in the end you have one average time series. And we did like a random walk sequence, which was going on and on, always according to the same structure, 2 different types, right? So what you see here, this is the real reliability, how it changes. Again, here you see the same thing, right? That's the sort of real, what the physical stimulus is doing. And what you see probably most pronounced here, but also in the others, is this is the ventriloquist effect, right? So you would expect that the ventriloquist effect, if participants really just use the sensory reliability at the time when the sound is presented, you would expect that this follows exactly these things. But what you can see is it's shifted, right? You have the ventriloquist effect here is smaller than what you expect. Why? Because you have a lower reliability beforehand. Higher, sorry, auditory weight goes up. So higher reliability beforehand. And later on, it's again like shifted. And the same also here. It becomes probably more prominent when what we did now, we flipped those ones apart, right? Now, if they were completely symmetric, they should be one overlaying the other. But what you can see is like, when you go in one direction, it goes always down, and then the other direction when you come back, which is the second half of the experiment, it's the other way around. So this demonstrates that all models so far haven't accommodated this, and indeed the reliability that the brain uses is learned over time, and it adapts to the reliability. So if now suddenly it makes also sense when you are sort of driving your car, and suddenly there's some fog, right? Then if the fog becomes progressively like worse, then you will sort of like basically lag behind, right? And use basically the reliability of the previous things as well. Good, so this is it. So just to, in the first part, I've demonstrated like temporal binding and predictions. Yes, the brain is indeed a prediction device, and cross-sensory predictions and prediction errors enable it to determine whether or not signals come from a common source, and especially for action, naturalistic, I would say, statistical action stimuli, there might be a forward modal instantiated in premotor cerebellar circuitry that helps you basically to, and can be trained to make this sort of multisensory binding. In the second part, then, we focused on the Bayesian causal inference, in particular for spatial localization, and focus on spatial disparity as an important cue. And here we've demonstrated that cortical hierarchies perform Bayesian causal inference by encoding multiple spatial estimates. And finally, in the third part, we focus basically on the sort of dynamics of Bayesian causal inference. How does Bayesian causal inference adapt over time? And we've highlighted here two aspects. One is that the common source prior, or the tendency to bind sensory signals, adapts to the probability of the congruent stimuli. And secondly, that the sensory reliability is not instantaneously inferred, but the brain uses the past to predict the reliability of future signals. And with this, I'd like to thank you for your attention and all the great PhD students that have actually done the work. And also, oh, these ones I haven't shown. These are the layer-dependent profile from Leipzig. Okay, thank you very much. Any questions? Ooh, I talked too fast. No, there's some question.
So I'm just getting clarification on this, but it seems like you had these two different models. You were, I don't know if you're like contrasting them or proposing, but could one look at it and think that kind of the default is to assume a common source, and this sort of late frontal thing is basically kind of when the system's detecting that maybe there isn't a common source, and it's kind of like a gating operation. It now decides to kind of feed back and say, you know, actually consider the possibility that there are two different sources. That would be kind of a hybrid of your two models, it seems like that. You have the default one, and then you override it when there's enough evidence to suggest that you have two different sources.
Well, you think so because the activation is higher in the DLPFC when you have, basically when you need to segregate, right? Rather than when you integrate.
That's right.
Yes.
It's kind of kicking in at that point to basically override the default, which was to assume a common source.
It's an interesting perspective. Yes, on the other hand, I mean, it's a question like how does it, I mean, I think it's a question about how does the dorsolateral prefrontal cortex code this, right? If you think that, yes, more activation that's the only time when the DLPFC is coming into play, then this is correct. It's also, the other thing is also like that, of course, in the experiment where we had like judging whether it's a common source or an independent source, that's also different from than reporting what you perceived. So when you explicitly judge, I suspect the activation will be the same. Actually, yes, it was the same, right? Whether it's congruent or incongruent, there's no activation difference in this one. Do you remember, like so there was this where I didn't show actually any activation differences. So in this paradigm, basically, if you look into the DLPFC, you don't have any activation differences. But here, the task was an explicit causal inference judgment. While in the second one, where it was more like forming the phonological representation, there, what was it? Here, there indeed we have more activations when you for the incongruent to the congruent stimuli. And indeed also like if I think back about my semantic experiments, when you have, when you need to sort of report the visual or the auditory and you have some interference, then the DLPFC, often of course together with the AC, with the anterior cingulate, shows increased activation. Yes, so I would say, yes, you're right, if there is some sort of incongruency, it becomes more activated. But it could also be that these are all special paradigms in the way that we also not only generate an incongruency, but we also generate like incongruency of different cues. So for instance, like the temporal synchrony here, in Magwerk trials, they're roughly temporally synchronous. So the temporal synchrony cue gives you in this one the impression that the two signals come from a common source, and then the phonological information gives you the information actually they come from different sources. So in this way, that's also like difficult to know what exactly. So I think we need more studies to define really what the DLPFC does in the causal inference. So I do think it plays a critical role in the causal inference, but it's not yet clear that it really does only the sort of error detection, I would say. I would be cautious about that. Yeah.
Thank you for a terrific talk. I have a question that's going to bump it up several levels beyond the work that you've done, and perhaps it's not even an interesting question, but my question is this. I'm really struck with the learning that you show, and I wonder how abstract that learning is. So in each case, you have an auditory and a visual signal, and in each case, the learning is about that particular auditory and that particular visual signal, and whether they're coming from the same or different source, right? So the question is, if you primed a participant with one of these, could they then keep the same Bayesian probabilities that they had learned and take it to another auditory signal, for example?
That's an excellent question. That's what we actually want to pursue in, for instance, like mixing the Magwerk effect with the ventriloquist effect. So you could, for instance, use like congruent phonological stimuli and demonstrate that they were effective by demonstrating that you have more Magwerk stimuli, more Magwerk effect, and then you present like something which is like a ventriloquist stimulus and check whether you generalize, right? And then also like what does it generalize across, right?
Exactly.
Does it generalize, for instance, like if you change suddenly the color of the stimuli, I would think yes, it generalizes, right? But if you have like a complete, it's a question like whether people think this is a new context or whether it's the same context, I could imagine. But I think it's excellent, we don't know yet.
Yeah, good, thank you.
Very nice. For those of us who are not brain people, who use the brain as sort of an abstract object in our analyses, we always see people reporting that this area is involved in X and this is involved in Y and so on. IPS3 and IPS4, I mean, those areas have been implicated in other tasks, in other experiments, in other kinds of things. Is there a commonality? So what is IPS3 doing? I mean, in your case, you gave us an interpretation of what's happening there. But that area seems to show up in many other kinds of experiments. Does it have a particular function, this area, that is true across many different kinds of tasks, many different kinds of experiments?
Yeah, so I do think that the IPS is very important for prioritization of information. So in our case, like spatial priority map, I would say. And I think there's a vast literature showing something like this. But I also believe that it's not like each region does one job, but it really depends on how they interact with other areas. And that's actually also one thing that we want to move towards effective connectivity analysis. So depending on, I mean, the question is like, is there one core function, and then depending, which is quite abstract, like a very, very, very tiny little component function sort of, but depending on which areas they interact with, they use this then to do different things, right? I mean, this is, I think this John Duncan's theory, right, about the DLPFC basically just like being good at many different things, right? And you could say probably very similar things to the parietal cortex, right? So, but I do think that this prioritization, which links to the attention, to intention, also to reward learning, right, is probably something which is quite often an aspect of many different tasks where you show this. And also like that is, for instance, what our work also shows that, yes, we do find some sort of like small multisense integration in the primary sensory areas, but I think our work predominantly, for instance, substantiates that there are primary sensory areas and there is association cortex. It's not all what people have been doing over the past century is nonsense, right? I think because people, there's work like showing like, oh, you can decode this and this from primary visual areas, and I find this sometimes also a little bit misleading. Yes, you can decode many different things from different areas, but it's also like how well can you do this? So in this way, for instance, like I would say our results also demonstrate, yes, we do find some sort of like multisensory effects in primary areas, but there is something about association areas, and IPS is a classical association areas. So it does something that it basically integrates lots of signals, and it generates something which is relevant for behavior, I would say. Be it now spatial. I think, for instance, like you could also ask, like, let's assume we hadn't used so the Bayesian causal inference model is of course quite generic. We could also apply it for Magwerk stimuli, right? And now that's a question like, do I believe that if we do the same manipulation but use like phonological dimension, or we use like a temporal dimension but it's about like phonological categorization, do I still believe that we get the parietal cortex out? I would think no. I would think that for instance, like speech recognition, where you sort of morph along the speech dimension, you would get probably more STS. So I do think the IPS is often involved in spatial stuff, right? And I think that's why we get the IPS. But on top of it, it's very important when you integrate signals and when it's something task relevant. These are sort of like 3 dimensions which I think are critical for the IPS. I agree that I don't believe it's like one specific function, but I think like if you think, okay, how is it connected, right? Why are there so many sensory signals converging there? That defines the function, I would say.
Well, this is not a criticism, but could it be a strategy? I mean, we usually do what we think we are good at, and we leave to other people to do the other stuff. But couldn't an important strategy in this enterprise be that if you have a hypothesis about what IPS and IPS 3 and 4 is involved in the tasks you've been looking at, to try and do an experiment, perhaps that's what you were saying a moment ago, or do research that moves away from the specific paradigm you looked at, and try to see whether, in fact, you can generalize an abstract function, a function, whatever it is that you're postulating, across different types of experiments, across different types of domains, across... It seems to me that we tend not to do that, and there's a good reason. We're not good in everything. I mean, we have experts in particular areas, but isn't it a missing strategy that perhaps should be pursued more actively?
Yeah, I think it's a good suggestion. I think like John Duncan really pursued this a little bit with the DLPFC thing, right? And I agree that for many of those regions, we should probably think, okay, what can we find? I mean, also if you think about social processing, people always talk about the STS and so on, all these things, right? And we often are a little bit like blank out other fields, right? And are just happy with the function that we assign to that. I do think, yeah, that might maybe help us to understand better whether there are really specific sub-functions and how the different connectivity patterns might then modulate these sub-functions, right? Yeah. I think the other thing which I should also say, I mean, one problem probably also of this work is, I mean, we have only these beeps and blobs, and they were sufficiently challenging for audiovisual integration in the scanner. But from a Bayesian perspective, of course, like we talk like the brain is optimized for X, Y, Z, or it does something optimal, right? So for instance, the Bayesian causal inference model is always like, our models are wrong, right? This famous statement, but some are more useful. And of course, like that's also something where we are also a little bit more critical. So asking whether the brain implements multisense integration optimal. So we have to say in our hands, many times participants are suboptimal. Especially if you just have like undergraduates coming into the lab, they are nearly never optimal, right? And the question is now, is it that the brain is not optimal for the signals that we present inside the scanner? Because when I usually interacting with beeps and blobs, right? It happens very rarely to me that I find a beep and a blob somewhere in the world. And so that's also like something, I mean, surely the brain is not optimized for our experiments, it's optimized for the real world, right? So it's nice because we can control all this, but it's also like another important dimension where I always feel a little bit ambivalent, right? We have at the same time, I like to have control over the stimuli, and that was certainly something which I loved about these bleeps and blobs. But of course, on the other hand, you ask like, is this really generalizable to what happens out there in the world, right? And that's also like, when asking like, is the brain optimal at multisense integration? I find it's, I try to avoid this term nowadays, or just like asking, like writing papers like, what makes the brain optimal? Yeah.
Trying to, in my mind, put together this finding, where you have this very immediate context effect on the probability of hearing the fused percept or not. Put that against the my own, I guess, phenomenology that, you know, no matter how many times I have taught the Magwerk Effect, I still hear the fused version. So it seems impenetrable in that sense.
For you? Oh, okay.
Yeah,
Magwerk Effect.
like many illusions, it seems impenetrable to my cognitive knowledge about it. And the only way I don't hear the Magwerk Effect is if I close my eyes. So I guess I'm wondering, are the subjects doing the equivalent of closing their eyes here?
No, I mean, so first of all, the Magwerk effect is actually not very strong. We had to optimize our stimuli because the bar-car stimulus, or the bar-gar stimuli, which is always like the classical example, doesn't work for many people. Like, so for some, P and Q works better, for others, like P and K works better. So it's like very variable across participants. Also, the Magwerk illusion in general is very, very variable. So for me, I'm very good at just constantly avoiding those. I think multisensory illusions are much more variable across participants than unisensory illusions, and also much more flexible for modulating. So I'm surprised that it does. And also you have to, yes, it's right. But if you think about like the modulation, right, it's not so strong. So if you say you can't help, this is like a small, it's significant, but it's small, right? We go from 0.7 to 0.68. So most of the time we would still have the Magwerk illusion, right?
But I guess I'm asking what you know, what your data could tell us about how that reduction is happening, and whether or not it's actually something at the level of weighting these signals differently versus something strategic to not look at the mouth.
Oh, no. I'm sure that. The other thing we should also say, we deliberately also fine-tuned also the noise in the stimuli so that you were at an intermediate level. Maybe I should also say that. That's what I should. So basically, in order to find a modulatory effect, you don't want to have like a very, very strong Magwerk illusion, and you don't want to have a very weak Magwerk illusion, but you always want to have in the psychometric function to be somewhere in the middle, right? Because then you will have, then a small change will make will have a big impact, right? And so basically, we use stimuli that are sort of mostly fused, but not very, very tightly. While you talk probably about perceptual illusions that are so automatic that you can't resist anymore. But deliberately, we chose stimuli that were sort of intermediate. So I don't think it's like whether they closed their eyes or whatever, but it's more that indeed, by design, our stimuli were such that you had like a stronger effect. Like also like with the ventriloquist illusion. Here, you also adjust the audiovisual disparity for each participant such that you are sort of intermediate level, so that you have basically the ability to modulate it.
Do you have time for one more?
Yes, we have time for one more, yeah.
I wonder, just your speculations, do you think that the mind is furnished to notice temporal and spatial fusion for some perceptual signals better than for others? So for example, vision and audition in identifying that it's me speaking and not Richard, or that I'm saying blah rather than, for the Magwerk or the ventriloquist effects. Is that something that's sort of more prone or more likely to be fused, vision and audition, than, because it helps you, you could think evolutionarily, it's going to help you locate the tiger. You listen, you look, but touch isn't going to be very helpful, right?
Yeah.
By the time that happens, it's all over, right? But so the question is, generally, do you think that the sensory systems, going back to the very general title of your talk, do you think that the sensory systems are differentially equipped to link up with each other over space and time?
So I'm not sure whether I would go that far that the sensory systems are differentially equipped, but I would think like it depends. You certainly train the systems, right, during neurodevelopment. Right. So if you present someone where auditory and visual signals never come synchronously, right? So I would think that basically because we are exposed to certain correlational structures, this will be encoded and this will basically shape. It's like I would think you generate basically a common source prior. That's how I would call it, right, from a Bayesian perspective. Through living in the world, you basically form various priors that are encoded in a neuroanatomical structure of how certain signals, how certain cells are sort of wired and how areas are wired. So, for instance, like touch and vision are, of course, like quite well linked when you explore things, right? That's where you need to have touch and vision. But auditory and touch very rarely are they correlated things. I mean, there are still like correlations. So you have like still like the touch can, for instance, like shape how you perceive sounds, right? So if you have like, I mean, there are these experiments where you have like either a rough surface, but then you have like a different sound, then you either perceive the surface differently or you hear the sound differently, right? I think Charles Spence also had this sort of this I think for which he got this sort of like this is the pseudo Nobel Prize, right? Where he basically had crisps and he made the crisps like sound differently, and then you thought they tasted completely differently, right? So all these things, but predominantly I think it's really like reflecting our environment. I could imagine if we were living in a completely different environment, then with a different correlational structure, right? Then we would also have like completely different multisense integration abilities. So it depends on the particular categories of stimuli and on the particular modalities.
A neuroscientist, you get a radical empiricist. So it's a totally empirical Sorry. Yeah, so scratch a neuroscientist, you get a radical empiricist. Assume that there's a learning story if it's a plausible learning story, but it's absolutely an empirical question. There could well be innate constraints here, or even innate mechanisms that use temporal and visual synchrony to localize objects. Obviously, if you lived in an environment, because of your learning effects, you're going to be sensitive to the correlations in the environment as well. But that doesn't mean that your environment is the source of these biases to begin with. And there's tons of experiments in the baby literature.
Yeah, so I wouldn't say that everything is like neurodevelopmentally, but I would say otherwise evolutionary selected. So for me, I think like priors either shape because of evolution, so then they might be innately
Sure, but that's
specified.
not evolution isn't the same as learning. Of
No,
course.
sure, sorry, yeah, but I would agree, I would completely agree with you. For me, these are priors, and priors are either because of evolutionary selection, right? And so because we've always been, I mean, also our predecessors have been living in this particular world, that's why certain neuroanatomically structures have been selected. And secondly, then there's this new development coming into play. No, so I completely agree with you. Sorry. Thanks for clarifying.
All right. Any more? No. Okay. Thank you very much. And we now have a coffee break, and we'll be back here at 4:15 for the last talk session of the day. Thank you.
You look like, but you disagree.
No, I just, this notion about that you had reliability signals so early and then you had this interaction, which I take it to be like a system deciding, oh, usually unreliability, I want to downweight that information, but actually if I start to suspect that it's from a different thing, now unreliability is like an extra cue, right?
So with the reliability, so you might be right.